support climate change, adaptation, and mitigation. So the first talk will be by Professor Frederick Fabry. So he's on a slow link today, so he submitted a pre-recorded talk, which I will be playing. Okay.
Hello everyone. This presentation on meteorologically driven complementarity between daily renewable energy resources at one location and demand at another is the result of a summer project by Joseph Samuel that I supervised. And basically it starts from the obvious observation that if we are to get our electricity from renewables, we have to deal with the fact that demand and supply are variable. In particular, energy demand has weather-driven fluctuations. For example, in the black curve here, we've got heat wave that generates a lot more cooling demand. And those are on top of daily cycles, weekly cycles, annual cycles, etc. In parallel, the renewable energy production, for example, solar energy in yellow or wind energy in blue, have fluctuations on their own that depend on whether it's sunny or cloudy or windy. Yet, renewable energy production has to fulfill most of our on-demand needs in a few decades, which means we'll have to store energy somehow. And that's going to require quite an infrastructure, which made us wonder if we are to lower energy storage needs, especially for longer duration, could more of our energy be generated when it's needed? And how would you do that? Well, you choose better sites for it that are not necessarily local. And the focus on this work is on minimizing daily average mismatches on the ground that, well, for example, my car battery could power my house for several hours, but if it's for a few days, then it needs to be produced from other sources at the time in question. And in order to understand that, why would that be possible? One has to realize that the same weather systems that generate peaks and valleys in demand at our current location also control renewable energy production here and elsewhere. So for example, we are in summer, and let's say you're in the middle of a heat wave. So where are you on this map? Typically, you'd be on the lower right. You'd be in the middle of a high pressure, it's warm, it's sunny, it's typically calm, and you're desperately waiting for the cold front in blue to the left to come. And when that cold front is going to come, it's going to get cloudy, a bit gusty, and then you're going to have colder air coming in and bringing you relief. So we have this pairing between heat and wind and sun. For example, if we focus on the lower right, we have the heat wave for 3-4 days of heat wave, and it's followed by the front that generated a lot of wind, and then after that, well, it calmed down. So when you were needing heat, or rather when you were too hot and you were needing cooling, where was the wind? Where was the sun? Not necessarily where you are. And because weather systems have typical sizes, shapes, and paths, we could determine, at least statistically, where renewable energy is more likely to be found when it is most needed. And the idea is based on the fact that we've often focused on local complementarity between demand and supply. When we think of solar and wind, we think of local solar, local wind. Yet in Canada, we're very used to have distant supply and sources. Quebec gets most of its energy from the northern province, and I'm sure it's true for other provinces. So why not think of renewable energy sources the same way? So how did we approach the problem? We started with a reanalysis of weather from 1979 to 2021 coming from the European Center, and it's processed at 0.5 degree lat-long resolution. From those, we are able to get curves below, like heating degree days and cooling degree days, that we used as proxy for daily demand. And we also then looked at solar radiation and estimated wind power at 100 meters above ground level, saturating at 15 meters per second, to estimate renewable supply. So we have a curve of demand and a curve of supply. And from those, we're able to compute correlations, not only correlations at the same location, but we can correlate the needs in, say, Montreal, and the power that would be available from a variety of places. So we generated those maps of correlations. So I'm going to start with examples of local complementarity. That's what we're used to. Upper row is winter, lower row is summer. On the left is solar, and on the right is wind. So focusing on solar in winter, we have high correlation on the eastern half of the country. So typically, when it's cold in winter, it's typically sunny, and that shows up in the correlation. At least in the eastern side of the country and the western side of the continent, except perhaps on the west coast, it tends to be more even. In summer, we also have similar pattern. Typically when it's warm, it's also sunny. So this is a good for solar power. For wind power, the complementarity is much poorer. It's actually negatively correlated. So typically colder days tend to be calmer days. Therefore, the timing of energy production by wind is poor in terms of its match with demand. That is, if you focus on local complementarity. But then if you start to look beyond the local, pictures changes. So for example, if we focus on Toronto in winter, and we saw that on average in Toronto, we have positively correlated, meaning that it's sunny when it's cold, but it's even sunnier in terms of timing a little bit in southwestern Quebec. So there seems to be a better timing there of solar energy when Toronto needs warmth. When we look at winds, we saw it's negatively correlated. But if we are to go to either the eastern maritime provinces, especially on the Labrador, or if you go in orography, actually not in orography, but it seems to be on the side of the valley, on the eastern side of mountain ranges, the winds tend to be much better correlated. Therefore, the production there is going to be much better timed to when Toronto is going to need its warmth or its electricity for warming houses. We can do the same exercise in summer, and as I saw in summer, we have decent correlation with solar energy on the top in Toronto, but if you go a little bit more to the south, it'd be even better correlated. And for sake of completeness, you can look at cooling needs and winds, and typically it's windy in Toronto when it needs cooling in summer. But if you were to go a little bit more to the northwest, you'd get an even better timing. So we see that we're able to get, at least statistically, better matches between energy needs and energy resources. This is for Toronto. You can repeat the same exercise for other locations. Here I'm just showing needs of heating in winter at Calgary on the upper left, Quebec City on the upper right, and Oklahoma City in the bottom for the sake of examples. And again, you can see that no wind is typically not good at your location, but similarly to Toronto and Quebec City, if you look to the northeast, you're going to find your wind, and it's normal because the weather systems that passed and bring you the cold wind, where is it then? It's in the northeast generating wind there. The situation is a bit different when we focus on Oklahoma City. Again, the better winds when they are cold, it tends to be in the east of the Appalachians, and also in northern Manitoba and Saskatchewan. And for example, Calgary, to the north of the provinces and also to the south in the United States, seems to be better timed. So this work suggests that there are regions whose renewable energy production will be better timed with energy needs than others, and hence it's more valuable economically. And we've looked at the possibility that climate change could change these patterns, and they changed them a little bit, but not significantly. So this is food for thought, basically, on how can you site better the energy supply, given that demand tends to be very focused in a few locations that may require or may suggest that some sites are better than others, not only in terms of magnitude of production, but in terms of their timing. Thank you very much, and have a good conference.
Thank you, Frederick. So Frederick is in the room, so if you have questions for him, he will be able to answer. So yeah, if you have questions, you can either write in the chat or you can also unmute yourself and ask the question directly. So we have one question in the chat. Which data did you use?
So we used era 5 reanalysis from 79 to almost essentially present. So 42 years of data that are used to generate these statistics.
Thank you, Frederick. I have another question: that how did you evaluate the climate change effect? That you said it was not significantly changing the pattern. We just started a garden.
So we looked at some forecast for the end of the century of the climate, actually, and how those. So we computed patterns for the climate models in the present and the climate models in the future. There's some slight displacement of patterns, but they aren't changing too much. And I don't know to what extent this is within the uncertainty of the model itself. But physically, it makes a lot of sense to have these patterns because they're based on the mechanics of weather systems, and though their intensity and number may change a little bit, the way they function should not.
Thank you.
So we have a few more questions. So one is, do you have any concerns about how the level of accuracy of the data would impact your results? That means if the wind data is accurate enough.
Well, we're looking for large-scale patterns, and it's an exercise in thinking. I mean, I'm not sure I would base an economic decision on that analysis, but it certainly, make you reflect on it. Instead of developing near-term prediction, this is a completely different issue, and I'll let somebody else answer that question.
Okay. So I think we can move to our next speaker, Charles Antoine Gosselin, which will be talking to us about an innovative methodology to understand the real cost of climate change on public sector infrastructure.
Can you see my screen?
Yes.
So hi everyone, my name is Charles-Antoine Gosselin. I'm a climate change economist working at WSP. I'm here on behalf of my colleague Yann Chavaillez, who could not make it, my former colleague Yann Chavaillez, who could not be here today. So today I'm going to present you an innovative methodology we've developed in order to understand the real cost of climate change on public infrastructure, on large portfolios of infrastructure. So I'll briefly describe the context of the research we've conducted last year. Then I'll go through the approach, which is really the main core of this presentation. Then I'll discuss some example of the results, and we're going to discuss on the main implication and what's going to be the next step of this project. So just to give you a little bit more of context, if we're looking at the timeline of this project, so in 2019, a member of the provincial parliament in Ontario asked the Ontario's financial watchdog to produce long-term cost projection on the impact of climate change on provincial and municipal infrastructure. So these information were unknown, and they were concerned about the fact that the cost of climate change might be significant and have implication for the taxpayers and citizens of Ontario. So the FAO, the Financial Watchdog of Ontario, the Financial Accountability Office, contracted WSP in December 2020, and we did this contract until last summer. And they came to meet us in order to establish a relationship between some relevant climate indicators and key infrastructure costs, which we will call today climate cost elasticity. So the reaction of the financial indicators with respect of a given climate variation. And recently, you might have seen past this in the news just before Christmas, and we expect 2 additional reports, but the FAO is publishing his results on the cost of climate change impact to public infrastructure. So the first report was on the cost to maintain and renew and replace building, for instance. And we expect additional reports to be published, I think, during this summer and before Christmas 2022. So the objectives of our work was to bridge a knowledge gap that we knew that existed. So actually, we cannot put a price either on the cost of climate change on public infrastructure, and we cannot neither put a price on the benefit that is related to make infrastructure more resilient. And when this knowledge gap is really tangible at the portfolio level. So for large numbers of infrastructure. So I think we're able to calculate this at, let's say, 1 or 2, 3 assets at a small number, but when we go to larger number, it's already hard to compute these results. So the project goal was to include the effect on climate change on the actual deterioration model that the economists of Ontario use. So we build, so here there's the project success factor that are listed there, but essentially we had to include the cost of rehabilitation, the operation and maintenance costs, the retrofit costs, and the renewal costs. And you've seen the table down there on the slide. You can see that this is the type of deliverable that we gave to the Financial Accountability Office. So we had to produce relationship that could express the variation of a financial indicator given a certain increase of, not increase, but the variation of a climate indicator, which we will call climate cost elasticities. And we did the climate cost elasticity with respect of chronic risk, which I will list a little bit after, but essentially it's for extreme precipitation, heat waves, and freeze-thaw cycle. So the actual model that the economists of Ontario use in order to project the cost of infrastructure works a little bit like this. I will not go through the detail, but you can see here the gray curve will represent what was the actual model when we started. So there's a deterioration occurring with the mathematical formula. So each of the assets are represented by a mathematical formula. And after a certain year, the asset condition, which is expressed by the FCI here, which is a ratio between 0 and 1 that expresses the condition based on the total value of the asset. So this condition is decreasing every year due to anything. It must be because of usage, because of its age, many reasons, but the impact of climate change was not accounted when these curves were developed in the 90s and the last decade. So with the impact of climate change, we expected, for instance, the deterioration in some case to be increased. So we thought that maybe when the asset could cross a little bit earlier, the reparation threshold and the renewal date could come a little bit earlier in its useful service life. That means that you need to pay a little bit more rapidly the cost that you need for repair and as well for replacement. Same thing when you have to repay for replacement. If you want to make your asset more resilient to climate change, you could expect a premium that you would pay because you need, for instance, to add additional equipment. You need to think a little bit more about the design. So such costs need to be included into the into the budget provision of Ontario's. And we took care of including these in the model. And we also consider the cost of operating and maintenance that could be related to climate change, because operating and maintenance is the cost that you need to pay every year. So for instance, if you think about the energy usage, this type of costs will be affected by the impact of climate change. So we started by building infrastructure archetypes. So what's a typical infrastructure in Ontario? What is this component? What is this subcomponent? What is the vulnerability of each of this subcomponent, and how can we express these vulnerability using climate indicators? So here you have an example we did for building. We actually covered 6 families of asset types. We covered building, roads, transit, bridges and culverts, stormwater asset, and wastewater assets. And we've looked at the interaction with 3 types of hazard that could be expressed by different varieties of indicators. So we've looked at extreme heat, extreme rainfall, and freeze to cycle, as I said a little bit before. So you can see in this case here for buildings, our archetype model split the building in 6 components. So you have the structure, the envelope, the mechanical and electrical system, civil infrastructure, landscaping, equipment, and finishing. And each of these components have an interaction listed with hazard, and this interaction is expressed by a given climate indicators. So we did a research in order to find which indicators could be the most suitable for this component, and we build a rational book about what could be the best indicators in order to express this relationship. And we use a lot of engineering standard to build this rational and to select the right indicators. So in order to produce this coefficient, what we did is that we had to do a huge data collection. So the information that in order to provide an estimation for the future had to rely on expert judgment, and I'll tell a little bit why later. But essentially for each asset interaction that I've presented in the page before, for instance, we knew that engineers will have a different opinion on what could be the cost of climate change. And it would be really intensive in terms of resources that we will need if you wanted to produce some really empirical evidence of these costs, and we don't necessarily have the time to do all of this information. So what we did is that we surveyed engineers and experts that worked in climate change resilient and expert in for these assets that I've listed a little bit before, and we've asked them to provide some estimation and of vulnerability of each of the components with respect of a given increase of climate change. So the information that they had to provide, for instance, we were asking them what's going to be the reduction of useful service life given an increase of temperature of X% with respect of this component or this subcomponent. And they had to provide a quantitative answer and as well as a qualitative answer, which we will call rational, which is the reason why they explain the mechanism, where they provide evidence from literature of why the financial when there could be a financial implication resulting from that. So that's how we proceed, and we use the data, the climate data from the Canadian Centre for Climate Services in order to provide this and other types of database. Once we collected the information, we proceed to conduce its statistical aggregation. So all the variation, the difference between the opinions of engineers and experts that we've surveyed here, we produce a distribution for these answers. So we did a PERT probability distribution function that gives us an optimistic, a pessimistic, and a most likely scenario of the vulnerability of the asset with respect of any climate interaction. Then we did Monte Carlo simulation using linear pool analysis in order to produce a final set of coefficient that we will call delta P, which is the variation of a financial indicator given a variation of climate indicators under a higher range projection of RCP 8.5 in future climate conditions, so between 2051 and 2080. So really long-term horizon. So I'll give you a quick sample of the result and how can it be used. So here you can see the example for a road, and you have the 4 types of coefficient, the financial coefficient that we founded here. And this is the expected variation of the cost under the scenario of Ontario representative. So we developed a climate representative scenario that is a little bit the average of the climate change expected for Ontario under our RCP 8.5 90th percentile at the long-term horizon. So you can see, for instance, if you look at the useful service life, we expect under a pessimistic scenario in the future condition, a reduction of almost half of the useful service life of roads, given the reduction mostly of the reduction of useful service life of pavement, but we also quantify the impact on road associated structure or road equipment and finishing. And you can see that we can provide a range for the economist of Ontario, because you can see that in the pessimistic, sorry, I think it's a little bit inverted here, but the optimistic scenario will be -41 and -48 for in the worst case scenario. So the economist can give a range to decision maker in order to plan for long-term capital spending. So I think one of the main findings and outcome that we found from this research is that the climate cost elasticity, so this method that we've developed, can be applied to large portfolios of assets. You might have seen this, but when they delivered the first result, the Financial Accountability Office, it gives number that we can discuss as a society, as government needs to plan for future and plan for long-term infrastructure spending. They need to have this information with them in order to make better decisions. So I think this tool here, this methodological tool, enables the government and large asset owners to do these types of analysis. The result also showed that the impact of climate change on Ontario's public assets are going to be significant. We've seen the impact with roads. We know roads are omnipresent. We can find them pretty much everywhere in the province, in other provinces in Canada as well. So this is a concern in terms of financial equilibrium. But at the same time, we recognize some limitation in the report that I will share a little bit after. So the relationship that we've developed are linear, so they are not really good to capture tipping points that might occur in the future due to climate change. So this is something we're working in order to improve our model. We have assumed a constant level of services, and we also compute the result based on cumulative climate costs. So for instance, we do the sum of the impact of extreme rainfall, heat wave, and freeze-to cycle, where sometimes there could be some dynamic where you could maybe only consider the maximum impact of heat waves, for instance, because if you want to improve the resilience of an asset, there might have been co-benefits for certain types of other assets. So thank you. I just wanted to say, if you want the full reference, you can access it on the Financial Accountability Office here. You will find the complete reports and the reports that are going to be published by the Financial Accountability Offices Ontario. And I just want to highlight here that this is a teamwork, and I've listed the team that contributed to this work. Thank you, everyone.
Thank you. Okay, so we have time for a quick question, if anyone has. Yes, Cami.
Bonjour, Charles-Antoine.
Bonjour.
Hi. I'm just curious. So I live in Newfoundland, actually. And what we see here in the infrastructure is that the road just lets go because of the topography and, just like it's landslide after extreme event that just let everything go. I'm just not sure I understand how this would be represented in your model. Would that be in the reduction of the lifespan of the infrastructure?
Exactly. So we need to put a little bit more context about how can we use this model. So this model is mainly to be used for budget planning, for financial planning with respect of chronic change due to climate change. So it's not made to project really localized impact of climate change, such as landslide or flooding or such thing. It's just a model that you can add to your normal deterioration model that any asset manager would use. So you take these coefficients that we've developed, you put that into your model, and then it gives you a little bit more flexibility in terms of capital spending, because you consider a little bit the additional expenses that on average you need to spend overall for your portfolio. So in your case, we could expect, for instance, that could be more landslide in the future. On average, we don't know where exactly, but if we can predict that, if we can plan for 20%, let's say, additional capital that we can save for future for these types of costs on average, then there is not going to be a situation where you need, for instance, to increase tax or just do weird financial operation in order to cope with the impact of climate change. So it's just making sure that the society is resilient in terms of economic perspective by adding this component in the usual calculation. I don't know if it's clear.
Yeah, I'm guessing. Does that mean then that right now the way the model is set up, it doesn't really account if you create more resilient infrastructure, right? It just tells you business as usual, ARR variable, and it gives you kind of the potential future investment that you might need in the repair and everything. But you don't right now have a comparative to, okay, well, if we build more resilient, might cost this much upfront, but you would be longer, right? That right now you're just in the first business as usual kind of scenario of the infrastructure.
I'd say no, because what we've developed, so we have if you want to, we have two sets of coefficients, for instance. One is called retrofit. So if you have an already existing asset and you want to just increase the level of services and make it resilient, but it's an already existing asset, then you need to spend a premium, let's say, when you do some intervention, and we capture this by our coefficient, and we have the renewal cost that is also captured. So if you want, for instance, to increase the captation of water for a given, let's say, civil infrastructure, then you need to spend an extra for this, and then this is captured by the model. But we did develop the model with the spirit of business as usual, but we have the latitude of using both scenarios, and I think the FAO is using both scenarios when they compare. So I think one of the main conclusions of the result is that it's probably worth to adapt instead of doing nothing.
OK. Well, thank you. Je vais être en contact avec toi dans le futur pour d'autres questions, si c'est correct. Merci beaucoup.
Merci.
Au plaisir.
Okay, so we're going to move to the next talk, which will be given by Amro Faki. So his talk is regional scale investigation of pile bearing capacity for Canadian permafrost regions in a warmer climate.
Yeah, thank you, Bernardo. Just want to make sure, can you see my slides?
Yeah, we can see.
Yeah. So hello, everyone. My name is Amro, and today I'll be presenting the study of bearing capacity of pile foundations for the Canadian permafrost regions in a warmer climate. This study was a part of my master's research thesis. So to outline this presentation, I'll first give a quick background and motivation on the topic. Then I'll move to the objective methods and assumptions. After that, I'll share the results for pile bearing capacity in the current climate and the projected changes. And finally, I'll give a quick conclusion and some limitation and future work. So to start with, according to the Intergovernmental Panel on Climate Change, the Arctic region will continue to warm at double the rate of the global mean. And even if this warming is limited to below 2 degrees Celsius, 25% of near surface permafrost is expected to degrade by the end of the century. This number would jump to 70% if greenhouse gas emissions follow the RCP 8.5 scenario. So the impacts of climate warming on buildings in permafrost are already being observed across the Arctic. Ground subsidence, settlements, cracks and deteriorations, and the weathering of foundations. Those can cause failures and even collapse of structures. But in this study, we will focus on pile foundations in permafrost. So piles, different materials of piles have been used across cold regions. For example, in Russia, concrete piles are more common, while in Canada, CSA recommends the use of steel piles, but nonetheless, wooden and concrete piles have been used in the past. So the forces exerted on piles embedded in permafrost differ from those of conventional piles. The equivalent of frictional force is called the adfreeze force, and it comes from the bond between the frozen soil and the pile. And in winter, another force is added, and that's the force coming from the refreezing of the upper part of the active layer, and it's called the heave force. So several studies have highlighted the possible catastrophic reductions in pile bearing capacity that is induced by climate change. For example, Strelitsky et al. And Sheklemanov et al. Modeled the bearing capacity in Russia and the North Slope of Alaska with the aid of global climate model outputs. And both these studies have pointed out that there is a need for more research on the adaptation of engineering and infrastructure systems to climate warming. In Canada's north, piles support many existing buildings and bridges, and there are already plans underway for several developments in the region. So therefore, there is a need to identify vulnerable regions from climate change perspectives to ensure the safety of infrastructure. That said, the main objectives of this study is to undertake detailed modeling of pile bearing capacity using a newly developed ultra-high resolution climate simulations, and to further perform detailed analysis on a corridor of interest. So to achieve that, this study utilizes the very first ultra-high resolution climate simulation performed over the Eastern Canadian permafrost region. The simulations were performed with a limited area version of the global environmental multi-scale model at a convection permitting resolution. So basically, two simulations were performed. The first one is a validation simulation driven by ERA 5 reanalysis for the 1989-2010 period, while the second simulation is the transient climate change simulation, which is driven by CAN-ESN2, and it spans the 1989-2040 period for RCP 8.5 scenario. So CAN-ESN2 is initially downscaled on this red domain here using GEM at 10 kilometers resolution, which is then used as the lateral boundary conditions for the 4-kilometer simulation, which is convection permitting. But now, since it's still hard to capture the surface heterogeneity even at 4-kilometer resolution, we performed offline simulations using the land component of GEM. So using GEM4 CAN-ESN2 as the driving data, we performed a 250-meter resolution simulation over the Slave Geological Grace Bay corridor here. This corridor is of interest in terms of infrastructure and resource mining developments. So the offline simulation enabled us to divide the soil column into 72 layers versus the 26 layers that were previously used in GEM. The equation we used to estimate pile bearing capacity comes from the Russian standards for soil bases and foundations on permafrost soils. The equation is similar to a conventional pile bearing capacity equation in the sense that there are two main terms, the end bearing and the adfreeze force or the friction component. What's different here is that we get more reduction factors and coefficients to account for pile materials or the building use, etc. Also, the value of the shear stress along the shaft of the pile here is taken from one of the several tables provided in the standards for different soil materials and different soil temperatures. Moreover, for our analysis, we used a 5-meter cement pile with 35 by 35 centimeter cross section. Now, the model we used has been extensively validated in Tufel and Sushama's study, but since the focus of this study is on permafrost regions, the validation of the soil temperature and the active layer is presented here. So the locations you see marked in this figure here are of point observations coming from the Global Terrestrial Network for Permafrost, Geological Survey of Canada, and the Circumpolar Active Layer Monitoring Network, and those will be used for the validation. So although the published active layer thickness observations are lacking, the available ones are shown here with colored stars next to the active layer thickness generated by GIM4 ERA5 and GIM4 CANISM2. And particularly for the continuous permafrost region, the simulations seem to capture the active layer thickness reasonably well. In terms of soil temperatures, the figure here shows the temperature at 15 to 20 meter depth from both simulations, and the filled circles here indicate the observed temperature at the depth of 0 annual amplitude. Those values are also captured very well by both simulations. So in this study, the depth to bedrock averaged at a maximum depth of 5 meters as shown in this figure. And keeping in mind that the used model captures the continuous permafrost extent and a transitional part to the discontinuous extent, in the current climate, the active layer thickness ranges from 0 to 5 meters, with the highest values seen at the southernmost regions of the continuous permafrost. Now, looking at the add-freeze force, the estimated value reached up to 2,000 kilonewtons, and that is in regions where deeper bedrock is present and cooler grounds. But if we look at the total bearing capacity, we see that values could be as high as 10,000 kilonewtons. For example, in the north of Canada, where the bedrock is very shallow and the ground is super cold. But nonetheless, for this study, regions with deep bedrocks are the most critical for the study. And you can see here that those regions can account up to 70% of the total bearing capacity. So comparing the results for the studied periods, if we compare the total bearing capacity, we can see a lot of changes, and that's due to the significant bearing coming from bedrock. So, but if we look at the projected changes to the active layer thickness, we see that an increase in the order of 1 to 3 meters for the southern regions here is projected by the end of 2040, which may result in the complete disappearance of permafrost in these regions for the top 5 meters of the soil, of course. While the northern regions are expected to have less than 0.5 meter increase in the active layer. The projected changes in the add-freeze force for the 2021-2040 period suggest a 5 to 20% decrease for regions with shallower bedrock and regions in the middle of the continuous permafrost region, and up to 30% for regions with deeper bedrock and closer to the southern edges of the continuous permafrost. Now for the offline simulation, the depth to bedrock is more realistically represented, especially around water bodies here, since the resolution used is 250 meters. So the performed simulation was able to capture changes to the thermal state of near surface permafrost within the discontinuous permafrost region. Those were missed in the other 4-kilometer simulation. That said, for the current period, the active layer thickness around the Great Slave Lake here is projected to be between 0.5 and 4 meters. And for the bearing capacity, we also used a 5-meter pile since the region is mostly underlain by shallow bedrock. So similarly, no changes can be seen for the total bearing capacity. However, looking at the future, we will see that the active layer thickness is going to have increases to be as high as 4 meters around the Great Slave Lake and in the discontinuous permafrost, while the northern regions are expected to have less than 1 meter increase. In terms of the add-freeze force, the results suggest decreases up to 300 kilonewtons for regions with shallower bedrock and in the continuous permafrost, and up to 600 kilonewtons for regions with deep bedrock and closer to the southern edges. So finally, to reflect more realistic possible scenarios, such as in the case of river crossing. We used other pile configurations that are 5, 10, 15, and 20 meters long over 2 points, one northern and one more southern. For the northern point, the bedrock was at 41 meters, and the active layer thickness increased from 0.3 to 0.5 meters, with the steepest decreases occurring after 2025. In terms of the add-freeze force, the results indicate decrease between 20 to 25% for shorter piles and 8 to 12% for longer piles. For the other point, the bedrock was at 50 meters, and the active layer thickness was projected to increase from 1.8 to 3.9 meters. And when we compare the add-freeze force to the northern point, we'll see that results indicate more decreases. That is 28 to 35% for the longer piles. The 10-meter pile would lose up to 45% of its capacity, and the 5-meter pile would lose over 85% of its bearing capacity by the end of the study period. So to conclude, the high-resolution climate simulation enabled the development of pile bearing capacity estimate through detailed pile climate interaction modeling. The add-freeze contribution to the pile bearing capacity for a 5-meter cement pile was in the 10 to 70% range, and is expected to have 10 to 30% decrease by the end of 2040 for RCP 8.5. And had we used a steel pile, we would see the similar percentage of reduction, but with smaller values of add-freeze force. And finally, the offline simulations at 250 meters provided us with detailed information for the slave geological grace bed corridor due to the better representation of the surface heterogeneity. Now, some limitations, the simulations performed only until 2040 because of the high computational costs. And in the future, we should consider longer durations, other scenarios, and driving GCMs to better quantify uncertainties. Also in the future, higher resolution geophysical fields would add a lot to the study. And finally, the developed framework can be used over a specific site for engineering analysis. In the end, I would like to thank Calcul Quebec and Compute Canada and Innovation Canada and finally Transport Canada for providing the computational resources and funding this project. Thank you everyone for listening, and I'll be happy to take any questions.
Thank you. So any questions for Amra? Okay. If there are no questions, it's time for a short break. So we will be back in about 6 or 7 minutes.
Thank you.
So we are ready to resume our session. So our next speaker is Muna Yunis, who will talk to us about building climate interaction modeling for permafrost regions to inform climate responsive designs in a changing climate.
Can you see, hi all, can you see my screen?
Yes.
Okay, perfect. Hi everyone, my name is Muna Yunis. I am a PhD candidate in Civil and Environmental Engineering at Western University. So today I'm going to talk about building climate interaction modeling for permafrost regions to inform climate responsive design in a changing climate. I would love to start by acknowledge my colleagues Bernardo and Masarat and my professor supervisor Girma and Professor Laxmi for their contribution to this study. Just to give a general idea about of what to expect after from this presentation, I'm going to talk about design sustainable and resilient buildings in permafrost regions using computational fluid dynamic analysis in a building information modeling environment to come up with a responsive design solution. And this is the phase 1 of the study. The second portion of this study, I'm gonna talk about just giving a hint about climate change condition and what we are doing work on in progress about high resolution climate models. So I will jump into the introduction. I'm just giving a background why we are focusing on that area. Basically, as you can see at these pictures, we have a lot of infrastructure defects at this region. As you can see in this picture, this building suffers from structural problems. Most probably it's differential settlement in the foundation caused this building to sink and tilt. Also, this building tilt. The other picture shows that there is the huge crack, structural crack in the foundation slab, in the foundation slab of this house. Another one that because of the soil unstable underneath this building, causing structural crack and windows breaks of this building. Although this building is raised a little bit above the ground, but it's immediately developed after construction, a structural crack at the concrete walls. So the takeaway message from here that it's clearly that the current design practices for these regions didn't consider the environmental load realistically. And on top of that, there is a lot of literature review recently shows that what is the real situation at that area, that we have a housing crisis at their area. And this survey made in 2019 shows that one major housing problem in 2019 ranged from 30% to 90% in Northwest Territories, which is a huge amount. Another survey made that compare the cost of permafrost damages to the value of the assets shows that buildings have the highest value at risk with 32 relative to the current asset value, which means if we need to maintenance or we have any problem in our buildings, if we need to retrofit, that maybe cost us 32% of our house. So this is a kind of why this is important to focus on our research. And then we decide to work on that area. And from literature review, we found that we can't address, we can't neglect these 4 elements. In my research, this is a simplified, honestly, chain. But in my research, there is sub-chains under each chain. So what we need to do to address this, to design sustainable and resilient building design, we need to address all these 4 or basically all these 3 together, because those are interrelated phases of the design in that area. So what we did, we looked about the climate, wind, snow, permafrost, and we did extensive research at that area to understand what is the wind profile, what is the reference velocity, what is the length scale, intensity, and then we looked also what is important of the surrounding condition, if we have any how the cities are planned, or does that they have a lot of building around, or they have trees that kind of block the wind or the snow. And the foremost and foremost thing or important thing to do or study at that area is the thermal analysis, because we are talking about permafrost. And we need to address the thermal analysis from 2 perspectives, for the house or for the house surfaces and for the soil underneath. And then we can come with a criteria, say, hey, this is our guidelines that we are used for this climate region. So again, just to give an idea what we did, we bought a lot of solution for that area, and we discussed, and then there were many challenges to come up with what is the best solution. We have to work on it. Basically because the northern community has harsh climate. It's different than other climate because they have cold climate because they have permafrost. Another thing, it's remote community and the houses is very expensive. So to come up with the active method, it will increase the houses prices there. So we decide to go with a most economical solution, which is to raise the building above the ground certain amount, and this will create a gap, will allow the air come underneath and carry the heat and taking away from the house. But within this solution, first we have to know what is the optimal height for each city in the Northwest Territory. This is for our priority. And the second thing, when we raise the building, this may be not the optimal solution from sustainability perspective. And we don't want to address one point and create another problem in the houses. So because when we raise the building, that we will increase the subjected area for the wind, and also the wind profile will be different. So we need to make sure how much we can, so how much that the energy consumption will increase and what we can do for that. So mainly the general scope of this study, that developing a modeling framework to determine infrastructure impacts on ground thermal regime for permafrost regions. Also assess the northern building behavior subjected to different environmental loads, integrate sustainable and climate resilience building design process and a building information modeling based environment to facilitate practical application, and inform the design of sustainable and climate responsive building by contributing to the northern building design guidelines. I will jump now to our methodology. What we did, we looked into, we used first of all, Equalite as a city in Nunavut territory to represent the climate data. And we looked about the Equalite and we found, we choose an area beside the airport. And we found this is the most common building shape they use there in that area. And we took the real dimension of the houses. And then we draw it using BIM tool, and we feed the model with a certain amount of information, which is 100 level of details, to use it in computational. That's what we need actually for our CFD analysis. And then based on the literature review and Environment Canada, we choose what is the soil layers and what the heat flux of each soil layers, and we developed this conceptual model. And then we use relatively new in CFD analysis, that convection and conduction, the same analysis in the CFD. So for when we are talking, I really have to mention here, when we are talking about CFD analysis, we need to make sure that our analysis is accurate. So basically, we start our analysis by taking our setup and make sure and validate our result with previously computationally and experimentally studies. So I will not go into details, honestly, into details of the validation, because this is first of all is well written in Kashi et al. Paper, and I'm running out of time. So basically, what we did that we come up that we use SSTK omega turbulence closure model, because it gives sufficient accuracy in the building surfaces, and it's able to capture the flow characteristic near the walls. Also, for our CFD analysis, we use CFD guidelines and literature review to determine what is the optimal size for our computational domain. And we divided our domain to 4 subdomains, and the nearest domain, it has for example CP4, it has the finest mesh inside, and we performed grid discretization using the setup that recommended from CFD guidelines, and we found that until we reach to the mesh, that the result will not change again after this mesh. So we adapt this mesh setup inside our old simulation, and this a bigger picture about what is how the mesh around the building, and we use 10 prism layer to capture the heat immediately beside the building. And this is a vertical section in the computational domain, shows that how is the mesh looks around the building and soil profile. Again, our boundary and initial condition, this is a vertical section in our computational domain, and this is our boundary. We use velocity inlet, symmetry plans for them, for the top and sides, ground for the ground and outlet pressure, and we defined our boundary wall and make sure to create interface between the soil layers. And this is our equation, how we estimated convective heat transfer coefficient and log law for the wind law, the epsilons, what we used for it. And we make sure that our Y plus is less than 5, because the literature review that shows us that it's the recommendation from literature review to use Y plus less than 5 to have an accurate CFD analysis. So I will move now to our result. So our result, it has two perspectives or two sections. That one focus on the building surfaces, or the CHTC for building surfaces. And why CHTC? Because it's the dimensional quantity that give us an indication how much the temperature of the building, or how much the building will lose energy or heat. And the other perspective or other section of the result will focus on the soil profile, thermal regime of the soil. As you can see at the first picture here, each time we performed a lot of scenarios to give an idea or insight for different regions or cities in the Northwest Territories, based on their weather condition, their wind speed. They can find here in this result, if they want to raise, for example, the building 2.25 meter, and they have 1.5 meter per second, the wind speed. This is what is the expectation that to have in the windward phase, the CHTC. As you noticed here, when we raise the building from 0.25 meter to 1.5 meter, that the range of CHTC is in the blue, that which is mean we have low amount of CHTC. That does what does that mean? That we don't have a lot of heat losses from that building, which is good. But don't forget that 1.5 meter per second, that our velocity. So that we can, what we conclude here for any city in the Northwest Territories, if we have less than the velocity 1.5 meter, and less, that doesn't matter if you raise your building a lot, we will not have a lot of energy consumption. If we look, this is another scenario, 3 meter per second. If you raise the building from 0.25, it's matter, start to have matter. We have the CHTC around the 20. So we have, it's concern us when we have more velocity, and then the result of 4 and 5 demonstrate the same. The last one shows when we have fixed height above the ground, what is the effect of wind velocity on it. And this clearly also shows where is the maximum heat will be, which is around the edges and the separation point, and in the red. So I will jump now.
You have about 2 minutes left.
Okay, I will. Yeah. This is the same idea when we are talking about the floor underneath the floor of the building. We have the same idea, just like windward phase. And this is, if I'm jump to the temperature distribution for the soil profile, we can see when we have 0.25 meter elevated building is not a sufficient height above the ground. There is a lot of heat will transfer from the building to the soil. And when we raise the building more and more until we reach 1 meter, 1 meter gives us promising results. Because it's wash away the heat distance after the building. And this is just like horizontal. This is a vertical section in the soil profile. This is a horizontal section at the top of the snow, just to give you an idea where is the heat will be under the building, how the heat distribution above the snow. This is another also another selected cases. Is the same idea about the soil. And here I compiled all the results in the figures. Is the same idea about what we saw previously in the soil profile. So in the summary, wind speed and direction significantly affect the ground thermal regime, the permafrost regions. We come up that a building of height 1 meter above the ground is the most suitable one for northern climate. Probably insulated floor section should be designed and specified to minimize building heat losses. And we need further studies to investigate the effect of snow drifting in structure. And I will end my slide here. We are working now on climate change using climate interaction modeling. And I have to acknowledge again here Professor Laxmi and Bernardo for their high resolution models. And yes, and this is end of my slide, and those are my references. And I'm happy to take or answer any question that you may have.
Okay, thank you, Muna. So we'll keep questions maybe for the end of the session. We'll jump right to our next talk, which will be given by Ahmed Sweater, and it's about cold energy storage as a solution for year-round renewable artificial ground freezing, a case study of the Giant Mine remediation project.
Thank you so much. Can you hear me?
Yes.
Okay, I'm gonna share my screen right now. Please let me know if you can see my screen.
Yep, yeah, we can see it.
Okay, thank you so much. Welcome everyone. My name is Ahmed Zaiter. I am a PhD candidate in the mining department at McGill University. My supervisor is Professor Agustus Mito. Thank you so much for attending my presentation titled Mathematical Modeling of Artificial Ground Freezing Systems for Mining Industry, especially for the case of the giant mine. So here's the layout of the presentation. There are two main sections. I'm sorry, I'm very sorry. I'm very, very sorry. Yeah. Okay, I'm sorry, like that was the wrong presentation. Okay, so the same introduction. My name is Ahmed Zaiter. I am a PhD candidate at McGill University. Thank you for attending my presentation titled Cold Energy Storage as an Adaptation Solution for Renewable Artificial Ground Freezing Case Study of the Giant Mine Remediation Project. And as I have mentioned, I am PhD candidate in the mining department at McGill University. So here is the layout of the presentation. I'm gonna start with the introduction, followed by conceptual and mathematical methodology. After that, I will discuss the results and end by conclusion as well as future work. Okay, so this presentation is about the giant mine. So the giant mine used to be one of the major economic forces of the Northwest Territories throughout the second half of the 20th century. Particularly, it has produced 7 million oz of gold made from 20 million tons of ore. Nevertheless, despite all these economic benefits, more than 200,000 tons of highly toxic arsenic dust were created, and they were stored in underground stopes and chambers in 4 different areas, as shown over here. Now, in the past, by the middle of the 20th century, these chambers and stopes were securely surrounded by solid, impenetrable permafrost, so they were contained within these stopes and chambers. However, due to global warming as well as mining activities, permafrost thawing has accelerated, which has caused the arsenic to leak outside the stopes and chambers, and this has posed several environmental as well as social issues. At the environmental level, we can see that these stopes and chambers are located alongside the shoreline of Yellowknife Bay, which is connected to the Great Slave Lake, one of the largest freshwater resources in Canada. And because of all of this contamination, the First Nation people who live close to the mine, has suffered significantly from these contamination issues. First, they have suffered from the scarcity of fishing resources along the Yellowknife Bay, as well as freshwater resources. Furthermore, there has been several reported illnesses, as well as a case of demise in the last century due to the consumption of arsenic. So for all these reasons, the Canadian government has initiated the Giant Mine Remediation Project in collaboration with Yellowknife's Dean First Nation to encapsulate the arsenic within the mining stopes and chambers. The industrial teams have investigated a lot, and they have decided that using artificial ground freezing is the best way, the most reliable way to contain the contaminated dust. So basically, in artificial ground freezing, what we do is that we freeze the ground around the contaminated dust, and this acts as a barrier. And so after choosing artificial ground freezing, the industrial teams have conducted full-scale field tests to investigate different AGF technologies with the following objectives. First, to complete the freezing process within the desired time scale, and second, to minimize the capital as well as the operational costs. So you can see a full-scale field test conducted over more than a decade around one of the arsenic chambers, and you see over here several groups where each group indicate a different artificial ground freezing technology. One of the main findings was that using the thermosiphon technology, is an attractive solution because of the natural ability of thermosiphons to utilize cold wind to freeze the ground in winter seasons. So as you can see in the figure in the left-hand side, a passive thermosiphons contains a working fluid, it's mostly pressurized carbon dioxide. So this working fluid extracts heat from the ground, evaporates, flows all the way up to the condenser, where it releases the heat to the cold wind, and then it condenses back to the ground. Now, in large-scale artificial ground freezing applications, passive operation during cold seasons is not enough. Therefore, a refrigeration system is added, as shown in the figure in the right-hand side, to operate thermosiphons in warm seasons as well. And such type of thermosiphons is called hybrid thermosiphons. So, when conducting literature review of thermosiphons, we can see that in the old by 2003 to 2011, the thermosiphon was assumed to be as a superconductor, and then a more accurate model was developed by Zhang in 2011, which has been considered a lot in the literature. And in 2021, I have developed a novel model for hybrid thermosiphons with mechanical units. And we have applied this model to investigate the capability of hybrid thermosiphons to freeze the ground in the case of the giant mine. And what we noticed that in our previous work, using a hybrid thermosiphon is energy intensive, as the total energy consumed can be as high as 3 gigawatt hour per year, which is like 1% to 5% of the provincial energy consumption of Northwest Territories. So for this reason, like in our project, we are proposing a year-round renewable artificial ground freezing system. Here's the conceptual methodology. We have two thermosiphons operating at the same time at some distance. The first set of thermosiphons are called primary thermosiphons, which are located in the vicinity around the giant mine, around the contaminated dust, to freeze the ground and contain the dust from leaking. The second thermosiphon, which operates at a nearby distance, it operates. Its main purpose is to create a pool of cold energy storage that will allow thermosiphons to run year-round using renewable resources, as we will see in the next slides. So in the winter seasons, the cold wind is able to run primary thermosiphons, as we see in the right-hand side. At the same time, the storage thermosiphons use the cold wind to store cold energy in the ground at some area in the vicinity. After that, in warm seasons, as we can see now, the storage thermosiphon is not active. So what happens is that now the cold energy stored by the storage thermosiphons is extracted through heat extraction pipes and transferred all the way to the primary thermosiphons. And this way we can run thermosiphons year-round without using mechanical refrigeration units. So to demonstrate our idea, we have used a mathematical model based on thermal network model as shown here, and it's based on thermal resistance of evaporation, condensation, as well as wind flow and coolant flow around the thermosiphon. So we have multiple conductive thermal resistances colored in green, in addition to convective thermal resistances colored in red, which is a function of H, heat transfer coefficient, that's determined using empirical correlation for condensation and evaporation. After that, we determine the overall heat transfer coefficient and the heat flux, and then we can find the heat flux across the wall of the thermosiphon. We have validated this model against field data from the giant mine test, which we have seen earlier. So we have selected basically group F, which contains 4 hybrid thermosiphons and 3 instrumentation holes. And the numerical results are validated well against experimental data, as shown in this figure. As for modeling of the heat extraction pipes, we have employed a computationally efficient semi-conjugate model. And this model, as we have, the computational domain is made up of the ground only, and we can see that only the ground is meshed. On the other hand, the coolant temperature evolution is monitored through a space marching algorithm. So transient heat diffusion in the ground is modeled using the enthalpy method, H, where H is the enthalpy, which is the sum of the sensible heat and the latent heat. Heat gained by the coolant is modeled using the first law of thermodynamics as follows, where small h over here is the heat transfer coefficient that is very carefully modeled using applicable Nusselt correlations that considers the development of the thermal boundary layer of the flow. So to demonstrate our idea, we have compared a system without cold energy storage, colored in green, with two of our own systems at different d, where d is basically the distance of the heat extraction, is basically the distance between the heat extraction pipes and the storage thermocyclones. So by comparing these two systems, we can notice that our proposed idea can freeze the ground of a lateral thickness of 6 meters 1 year faster than that without cold energy storage. Now, if we compare this system with another one that employs mechanical refrigeration, based on fossil fuel, and mechanical refrigeration would be superior. However, using our system, we are saving 3 gigawatt-hour annually, which is a great amount of energy. So, in conclusion, we have proposed a novel cold energy storage system to run hybrid thermocyclones year-round using sustainable energy resources. We have demonstrated our idea mathematically, and we noticed that using our idea, we can freeze the ground 1 year faster than passive thermocyclones without cold energy storage systems. And also, if we don't use mechanical refrigeration units, we are saving 3 gigawatt-hour annually. In our future work, we aim to demonstrate this idea experimentally and hopefully submit an invention disclosure on this idea. And then we are also aiming to conduct techno-economic analysis to investigate various capital and operational costs. So by the end of this presentation, I would like to thank McGill Tutorial Award, the FRQNT for their financial support of my project. In addition to industrial collaborators, particularly Numerous Technique Incorporation, as well as Chemical Corporation, plus our lab members. So thank you all for listening.
Thank you, Ahmed. So any questions for Ahmed? So I see 2 in the chat. So the first one, is your ingenious solution robust to expected large increases in winter temperature due to climate change?
Actually, that's also one of our part of our future work. Right now, it's a mathematical demonstration, but in our future work, we are aiming to have to integrate a climate model to our system to take into account climate change.
Okay, perfect. And the second question is, given more or less permanent aspect of warmer Arctic temperatures and an assumption that there's a desire for arsenic to remain isolated in perpetuity, to what extent is your system able to run for centuries with minimal maintenance?
Well, this idea, like in the industry, is supposed to the current proposal in the industry is 400 years. So basically the idea, so this system should be able to run for 100 years. And after that, there are no plans from the government. If I want to plan something, to be honest, I don't know what to plan, but like this plan works for 100 years. Like it's supposed to work for 100 years.
Okay, perfect. Okay, so we are ready to move to our last talk of this session, which will be given by Mohammed Robiul Islam. So he will talk about the climate resilience of dams and cliffs, perspectives from the literature.
Yes, thank you so much.
Hi, good afternoon to all. Can you hear me?
Yes.
It's perfect. And can you share my screen as well, right?
Yeah, we can see it.
Okay. Okay. So this is Muhammad Rabiul Islam. I'm going to present my work. I'm a doctoral student, doctoral candidate, Civil and Environmental Engineering Department at the University of Western Ontario. My talk about climate resilience of dams and levees perspective from the literature. So what is my background and motivation? So flood is most destructive disaster all around the world. If we focus on the last 2 decades, we can see steep increase the loss due to flood, catastrophic flood, mainly US and Canada. Here are some highlights. Levee failure in the Hurricane Katrina. When like 81 billion USD property is damaged. So yeah, the main region, like structural measures are not reliable to protect the damage from the excessive flood load. And here is another example, the dam overtopping due to the Calgary flood. One of the most destructive flood in the Canadian history, and the loss and the damage is accelerated due to the failure of the structural measures. Here is one of the recent British Columbia flood that associated due to the atmospheric river effect and flood walls and landslide, and also there's series of critical infrastructure that damaged by this extreme flood. So there is a big question, like how reliable are the traditional approaches for design flood estimations of the dams and embankments we have. But we need to understand what are the flood generating mechanisms in the Canada. There is a study by the Bartle et al. That we can see like rain and snowmelt are the most dominant flood generating factors all across the Canada. Mainly flood centered in the British Columbia and Alberta, Ontario, and the Atlantic region as well. So yeah, if we want to focus on more comprehensively, we have produced a figure where flood will where extreme precipitation, like daily extreme precipitation, will be increased end of the century under the RCP 2.6 scenario. That we can see every part of the country, the extreme precipitation will be increased. Like British Columbia and the Atlantic region will be experienced more precipitation than the other region. And if we focus on the existing dam infrastructure, like we can say Canada has more than 15,000 dams, among them 1157 are the large dams. And what are the previous flood history that the Ontario experienced about 49 flood disasters that associated with the most damages, like 8.6 billion damages of these provinces. So if we focus on this same scenario in RCP 8.5 scenario, we can see is this there is also British Columbia and the Atlantic region will be projected to experience more precipitation increase, about 30% precipitation, extreme precipitation increase. And as we know that the Quebec only accommodate the 50% of the dam, and four provinces like Quebec, Ontario, British Columbia, and Alberta accommodates more than 80% of the dams. And this region is also expected to experience more flood due to the climate change scenario. And the severity of this flood already have a big concern about already experiencing the climate change signal. So what are the usual design flood approach in the national and international scale? If we have measured two division, like one of the small dams and small and medium dams, and for the large dams. But the design flood mostly rely on the historical climatic variables, precipitation temperature, that's only the static variable. So no periodic updates, and that consider only the static condition. So what are the main limitation of the traditional process? If we see in the left side figure, that's from the Public Safety of Canada, we can see the largest spike of the flood disaster from the 1960. And so we cannot rely on the static parameter like climatic parameter, precipitation, temperature, evaporation, etc. This because it's the non-stationary, and climate change, due to the climate change, everything is changing. But why we cannot incorporate the climate model outputs? There is a large range of variability in the climate model projection, and another things on top of that is the course resolution. And in the earlier period, it was unavailable for all users. Like, but another thing, this is not this is not the last. We only focus on the deterministic approach, but deterministic approach cannot become a reliable solution. We need to focus on the risk-based approach. What are the design flood classification and the safety guidelines all around Canada? We like the regulation. Unlike the USA and Australia, Canada dam safety is mainly the provincial responsibility, and only 4 provinces, British Columbia, Alberta, Quebec, and Ontario, they have own dam safety guidelines, but it's almost mirror of the Canadian Dam Association guidelines, and other provinces directly follow the CDA guidelines, but CDA is non-profitable voluntary organization. This is not the regulatory body. If we focus on the dam classification, dam safety classification of the CDA, we can see they have classified dam based on the if the dam will be failed, how many lives will be lost, and what will be the impact of the direct damage. And we can see for the high and very high and extreme, we need to focus on the probable maximum flood that comes from the probable maximum precipitation. So what is the PMP estimation approach in the Canada and USA? There is a guideline by Water Meteorological Organization about different method of the PMP estimation, but Canada and US mostly they follow the storm maximization method, hydrometeorological approach. And but in this method, we can see that the precipitation efficiency and precipitable water for maximize the storm, we are assuming that they are independent. They for maximization, they will occur at the same time. But there is some recent study, they'll focus this will vary especially and temporally. They are not more independent, so they're dependent, and for the spatial and seasonal scale, they vary, their dependencies varied. So what are the uncertainty associated the design estimation procedures? We can see the range of uncertainty, and if we focus on the stepwise, like first measure uncertainty associated with the PMP estimation, like climate variability, non-stationary, and the moisture maximization method. And uncertainty in the probable maximum flood or runoff calculation associated with the continuous land use change and SONOWATER equivalent, flood routing equation, and the complexity of antecedent soil moisture. And finally, landslide or ice jumps always another level of uncertainty that may add the design flood estimation. So what are the main challenges for dams and levees in Canada? As I already discussed, like we are experiencing atmospheric river in the British Columbia. So most of the climate projection, they projected that British Columbia will be British Columbia projected to experience more atmospheric river-induced extreme precipitation in the future, and the hurricane and tropical cyclone also carry a large precipitation that we have already experienced during Hazel and Joan and Igor and so on. And another important thing, the gradual sea level rise, and most importantly, there may be the complex mechanism or the compound effect of this disaster may lead to excessive water load. Their concurrence event, like they may lead to excessive water loads to dams and levees. But what we have edge dams, small and medium-sized dams. So they're not. So they are not like they cannot provide safeguard against these excessive water loads. So we need to estimate, ensure climate resilience of dams and levees and embankments. So here we proposed a framework for climate resilience of dams and levees. This has the major 4 steps. Like step 1, understand the physical mechanism. So we cannot rely on only the statistical things or probability distribution. We need to understand how the storm generate, like consider topographical, hydrological, and atmospheric variable. And as we see that there is a flaw in the methodology, so we need to improve the methodology, and both for large dams and both for the small and medium-sized dams. We need to integrate climate sense to incorporate the non-stationarity and use large ensemble of regional climate model outputs, and incorporate the risk-based approach. But we cannot not rely on only the deterministic approach. We need to incorporate the risk-based approach, and we need to consider different combination of the antecedent soil moisture condition as well. So what is the conclusion? In conclusion, like Canada dam construction mainly risked in during the period 1950 to 1980, and now half of the country's dams more than 50 years old. So there's a lot of age dams, and unlike some other countries like Australia and USA, their PMP and PMF estimation have a generalized guideline, but in Canada we have not. So we cannot track our update of the PMP and PMF estimation because we have no generalized guideline. And due to the climate sense, the precipitation, extreme precipitation, and other drivers of the flood generation is increasing over the years. So we need to climate resilience of the critical infrastructure, mainly in the dams and levees, so on. Thank you.
Thank you, Will. So any questions? Well, if there are no questions, I want to take the opportunity to thank all speakers, and I invite you to join us for the last part of our session, which will take place in about 20 minutes. So thank you all, and see you soon.